Hello, everyone. Thank you for joining us today. Our project explores a compelling question in the intersection of healthcare and AI. The question is, can neural networks outperform doctors in glaucoma detection? This presentation is culmination of our work in deep learning. Our team is Edu, Delaram, Sophia, Gaurav, Tingyu, and Shinyang. Next slide, please. So let's get started with the project scope. We use the IPEG slide dataset from Kaggle, which includes labeled retinal fundus images. Our task was binary classification, predicting whether or not a patient has glaucoma. This problem has a number of practical applications, including early detection, enabling telemedicine, and enabling scalable screening solution, especially in resourced region. Next slide, please. So our primary evaluation metric was accuracy. However, in a medical setting, we must also consider false positives and false negatives. False positive waste healthcare resources, while false negatives are more dangerous. They result in misdiagnosis, delaying treatment. So while accuracy is important, minimizing these types of errors was also key in our evaluation. Next, please. To determine whether our model performs better than humans, we referred to a benchmark from a 2023 MDPI vision study. The lower threshold of ophthalmologist accuracy in glaucoma detection was reported around 70%. Our model's goal was simple. It is beat that benchmark. Next slide, please.
Here's an overview of the data set. There is 6,540 images in total. We had a balanced 50-50 split between glaucoma and non-glaucoma images. While the original resolution was 256 by 256, we resized images to 64 by 64 to streamline training during early modeling phases. Our dataset was split into 60% training, 20% validation, and 20% testing, using stratification to maintain class balance. Next slide. We began with the logistic regression model as our baseline. As expected, the model underperformed, with a training accuracy of 68.5% and cross-validation accuracy of 66.7%. This result confirmed underfitting and set a benchmark for more complex models to surpass. Next slide. We then implemented multiple multi-layer perceptrons, gradually increasing depth. Generalization improved as we increased model complexity. Model 3 achieved a training accuracy of 71.7% and validation accuracy of 67.9%, finally surpassing the 70% human benchmark, at least during training. Still, we had room for improvement on validation and performance. Next slide, please. We tested different learning rates to optimize model training. The best performance came with a learning rate of 0.001. Higher rates like 0.05 caused instability and poor generalization, confirming the importance of this hyperparameter in achieving reliable performance. Next slide.
Perfect. We also experiment with different optimization algorithms. Adamax performed the best, achieving highest accuracy in both training and validation. SGD was decent but slightly overfit. RMS prop underperformed significantly, showing it was not well suited for our problem setup. Finally, we evaluate the impact of training duration. More epoch generally improve performance. At 100 epoch, we achieved the best result, 76.5 training accuracy and 72.2% validation accuracy. This model suppressed the 70% threshold in both domains, indicating our neural network can outperform the average human doctor in glaucoma detection, at least under these conditions. To improve training stability and model performance, we explore different weight initialization methods. We use HE uniform initialization for all dense layers because it's well suited for ReLU activations. It maintains variance across layers, which prevent vanishing or exploding gradients. Additionally, all bias was initialized to 1, helping neurons activate in early training. As shown in our result, the improved convergence speed and performance. The best configuration reached a validation accuracy of 72.94%. We then introduced L2 regularization to tackle overfitting by penalizing large weights. We test 3 values of lambda, 0.001, 0.01, and 0.05. The best result came from lambda equal to 0.001, where we saw a validation accuracy of 71.56%. Higher value leads to underfitting, as shown by both lower training accuracy and flatter accuracy curves.
Next, we examined dropout. We tested dropout rates of 0.1, 0.2, and 0.5. A dropout of 0.1 yielded the best validation accuracy at 70.26%, suggesting it provides the right balance between regularization and model capacity, while 0.2 was close behind. A dropout of 0.5 drastically hurt performance, leading to underfitting. Next slide, we found that the combination, dropout, and L2 regularization provide the best overall generalization. As seen in the right-hand table, validation accuracy peaked at 70.87% for the model with dropout of 0.1 and L2 lambda of 0.01. This combined setup became our top performance MLP model and a strong candidate before we transition to the SNNS. Next slide. Batch normalization was added to further stabilizing and accurate training. It reduced internal coverage shift and smoothing learning. Our best model using batch normalization achieved a validation accuracy of 71.33%, over 6% higher than the same model without it. This combined batch normalization crucial role in enhancing coverage and generalization. I'll pass it to Ari.
So to prevent overfitting and avoid unnecessary computation, we implement early stopping. If validation loss didn't improve for 5 consecutive epochs, training stopped, and the best weight were restored. This method was particularly helpful for our RNN, where training accuracy reached 89%, but validation plateaued around 67%. Early stopping preserved generalization and saved time. Next, please. So after optimizing our MLP, we transitioned to convolutional neural networks. Our CNN had 2 convolutional layers with ReLU and max pooling, followed by dense layers with dropout and batch normalization. Using sigmoid activation at the output, this model achieved 71.94% validation accuracy, beating the human benchmark lower bound of 70%. This result confirmed the strength of CNNs for image-based medical classification. Next, please. And we also test a recurrent neural network. Even though RNNs are typically suited for sequential data, the model showed high training accuracy, nearly 90%, but failed to generalize, with validation at only 67.8%. Despite using dropout for regularization, the model clearly outfit. Ultimately, RNNs were not a good fit for static image classification, and our CNNs outperformed them. Next, please.
Therefore, after trying all these different neural network models, we decided to all go with this one that delivered the best performance. We turned the initialization for each layer, combined dropout and batch normalization, and trained over 100 epochs under the Adams optimization. It achieved a validation accuracy of 73%, outperforming logistic regression, RNNs, and most of the MLP setups. This model showed the highest generalization and served as a competitive alternative to CNNs in our experiments. Beyond technical accuracy, our model has clear operational benefits. First, it automates initial glaucoma screenings, significantly reducing the manual workload for ophthalmologists. This frees up doctors to focus on more complex or urgent cases, accelerating diagnostic workflows. Let's look at a cost-saving example. If doctors currently analyze 1,000 patients per month and each consultation costs $50, automating just 50% of those screenings would save 500 consultations. That translates into estimated savings of $25,000 a month, a compelling economic argument for deploying AI. There are also major benefits in diagnostic accuracy and patient outcomes. We observed that traditional logistic regression misclassified over 30% of the patients. In contrast, our deep learning model significantly reduced false predictions. Fewer misclassifications means fewer missed or incorrect diagnoses, and that directly improves patient safety. In real-world terms, this could prevent hundreds of missed glaucoma diagnoses every year. It also supports clinical decision-making and is crucial for scaling telemedicine with dependable AI screening. So overall, the impact is not only financial, it's clinical and strategic as well. Thank you so much for listening to our presentation.